this concept of completing the square, it's so important. I was teaching my Calc 3 class last night. All right, so let me just give you perspective on this. You're in Algebra 1 right now. Then comes Geometry, then Algebra 2, then Pre-Calc. Then we offer Calculus 1 here, which is an introduction to college-level calculus. After that would be Calc 1, then Calc 2, then Calc 3. So you're talking like second year of college math, assuming that you haven't broken the streak of taking math classes between now and then. All right, that's how far in advance you are. You're talking about like 20-year-olds, right? Ish. I went over completing the square with them last night. Right? It's a concept that never goes away. Right? Just like factoring never goes away, completing the square never goes away. So getting a good understanding of it early on will make a huge difference. Right? And when we incorporate trigonometry, we'll be using completing the square for that. You know, every level you'll be dealing with completing the square in some capacity. All right. So in number 1, we have the factored form. So the factors themselves would be x plus 1, x plus 1. Right? Just like the second one would be x minus 3, x minus 3. It's like busy work, right? It's like, oh, what possible use could this serve? An incredibly important one. All right, so we need to distribute. So double distributing process, x squared, then we'd have a 1x, a 1x, and a 1. All right, so then we'll need standard form after that, which is actually not really the standard form, but it's actually, here's something for somebody. The general form. Standard form is something else. So x squared plus 2x plus 1. All right. So basically we're unfactoring by grouping if you think of it that way. So the second one, we'd be looking at x squared minus 3x plus 9. So x squared minus 6x plus 9. All right. X squared plus 4x plus 4x plus 16. So x squared plus 8x plus 16. And then x squared minus 20x plus 400. So x squared minus 40x plus 400. All right. So this is an important table here because the follow-up is asking us if we see any patterns that might exist. And if you're not really looking for patterns, then you don't have your eyes open to it, you're not going to notice anything. Right? I'm not the most observant person in the world. It's like, hey, who are you talking to over there? I don't know her name. Hey, was that the lady with the strawberry blonde hair? I was like, I don't know hair colors. I don't know who this person is. Okay, well, was she wearing the brown boots? I was like, I don't look at people's feet. All right, well, was she wearing a blue sweater? I don't look at people's sweaters. And it was like, what do you look at? I honestly, I don't know. I don't know. I don't really acknowledge humans in general. It's kind of actually, this is probably not a good example. Yeah, I'm really, really bad. I don't, there's no retention there. So I would not be like, if the cops brought me in to identify, in a lineup, I'd be like, yeah, it could be any of them. They're all the same because I wasn't paying attention. So that might be you. You're looking at this, you're just doing it. You're not paying attention to what you're doing or why you're doing it. All right? So let me just kind of draw your attention to the facts. You may or may not have picked it up. Take a look at this guy, right? Yeah. All right? Yeah? And then this guy, right? Yeah. What's the relationship? Times 2. Is that consistent? Yeah. Yeah, it happens every time, right? Okay. Now, what about the relationship between this guy and this one? Times itself. At first glance, it might look like it's the same, but when you go through a few more examples, you see that it's times itself squared. All right. So if you're already given the factored form, then it's very easy to come up with the general form from that. But the double distributing process is not difficult. And in fact, just reflecting back upon the last 2 units, distributing, not too hard. The process anyway. Don't think about multiple choice questions because they're all like tricky in some capacity. All right, but just the concept of distributing out stuff, not too bad. Factoring is where things got tricky. Factoring is where we need the mnemonic devices and shortcuts and tricks. All right, so here's a trick. If I'm given something that's in a particular form, so let's say I have a quadratic. That's definitely, without a doubt, a perfect square. All right. So let's say I have x. I'll say plus a. I'll make it in general form, where a could be some positive or negative number. So a. I'll say, well, I'll just focus on integers for now, because it could involve fractions and stuff like that. But a belongs to the set of integers. All right. Funky E, funky Z. If you need to write out what that means, then by all means. A belongs to the set of integers. I'll bring it in and clean it up. So this is belongs. We'll only focus on the integers for now. All right, so the result, if you just follow the pattern that developed in the table, we'd have x squared plus what? Something x so I just need the something, and it's related to whatever this guy is, right? So to get the middle term in the expansion across the board, what did we do to the second term in the binomial? Times 2. Yeah, so if the second term in the binomial is a, multiply it by 2. All right. Now, the last one, that's just some kind of constant. How did I get from the 1 to the 1 and the -3 to the 9 and the 4 to the 16? Multiply by itself, same as squaring it. So a times a would be a squared. All right. What this tells us, it's really kind of nice. If you're dealing with a trinomial that's in this form, it's known as a perfect square trinomial. That's a poor quality A, so I'm going to fix that. Aw. There we go. Perfect square trinomial. I always felt when I was a student that those are like 3 words that were just shoved together. It doesn't sound like it's proper grammar, but it's a trinomial that's a perfect square. So we're calling it a perfect square trinomial. All right? So anything that follows that form is going to factor this way. All right? So we're going to cut to the chase pretty significantly. All we have to do is identify our A value. All right. So if I'm following this idea, all I really need to do is take a look at whatever this guy is. Well, it has to be twice whatever the A value is. All right. So I'm going to make an assumption if it's going to be in factored form, that it's going to be x plus 6. All right, because the relationship, if you want to study formulas, that's fine, but really just going back to the table, in our expanded form, whatever the second number in the binomial was, if we doubled it, that gave us the second number. So then the check comes from the idea that 6, when you settle on the 6, it needs to square to equal this value. So you're going to ask yourself, does it square to equal that? If the answer is yes, then you have the proper factors, and you don't have to go any further. So you're going to chop this bad boy in half, make that part of your binomial, but then square the result to see if it equals the third term in the trinomial. All right. So let's try that with the second one. So we have a negative 12 here. The sign's important. So I'm going to assume, I'm going to chop that in half. So x minus 6. So then I'm just going to ask myself, will this negative 6 square to equal 36? Yes, negative 6 times negative 6 is equal to 36. All right. What would the next one be?
X plus 10.
X plus 10 squared. After that? X plus 50. Then now I introduce some fractions. Not a big deal. X minus 3 over 2. Because there's fractions in here, we do want to verify. We don't want to take it on faith. Is negative 3 over 2 squared 9/4? Yeah, because when you square a fraction, you square the top and bottom separately. 3 becomes 9, 2 becomes 4. Yeah. All right, so what we get from this is a little addition to our rule above. Also works for the set of rational numbers. All right, rational, ratio, so fractions. All right, why am I bringing these terms back now? I'm going to bring them back repeatedly because they seem to like asking about them on the region. So, integers, whole numbers, rational numbers, natural numbers, that's all going to be there. We're going to have to review them. All right, so then we'll make an assumption on number 11, and this is where things start getting a little dicey. You might say x plus 4, because we're chopping it in half, squared. But then when you go to test the 4 to see if when you square it, it gives you a 3. Well, it's not going to give you a 3. So this is not the correct answer. All right. So it's at this point where we would need to do something else. So at this point, we could say that this idea of a perfect squared trinomial is going to fall apart. You might even say it's not factorable, but there are a set of factors that would satisfy this just using this topic called completing the square that we're going to learn about. All right, completing the square visually, when you did the Desmos activity on Monday, it was physically completing a square. All right, moving forward, it's going to be both. It'll be you completing the square physically, but also completing it algebraically, and I'll show you what that looks like. All right, so what's different about the last example in the table above? It's not a perfect square trinomial, which I'll abbreviate with a PST, perfect square trinomial. Now, if I could change that expression, I would. Specifically, I would add 13 to 3 to make it 16. All right, the problem is if you were to do that, so let's say I just wanted to do that. I started off with x squared plus 8x plus 3. Said I'm just going to add 13 to it. Is that a legal move? I'm asking the question so you know the answer. No, it's not. You can't just add something to a value. You're changing its value. right? So yeah, you can think of 100 different examples off the top of your head where, like, oh, I'll just add something to it. It's the same thing. No, it's not, because if that were the case, then everybody would have 100 average. Right? You just add X number of points to your test grade, and there you go. All right. So what we do is a sneaky little move here. I'm adding 13, but I'm also going to subtract 13. And what that's going to do is make the first four terms, when you simplify it, it's going to make that part of it a perfect square trinomial. And that part will be factorable to x plus 4. And so this would be our factored expression. All right, by completing the square. Now we're going to generalize this approach in a little while, just so you can get a firm understanding of, okay, how would we think to do this? Well, first off, I didn't even think to do this until somebody showed me. All right, there's a lot of strategies that you're going to learn moving forward where you're like, I never would have thought to do that. My answer to that is, well, then you're in the right class, right? Because there's a lot of situations where, you know, like, unless you're exposed to something, it's a very rare student that's going to be like, oh, I'll just add 13 and subtract 13 from the expression because, you know, math, why not? You know, it doesn't often work that way. There are exceptions to that, but in most cases, you need exposure to it the first time or two before you can really dive into it. So if you're like, I would have never thought to do that, neither would I, right? Neither would I until I saw it done. So graphically, you did this with Desmos, and it's pretty straightforward. Using a straight edge just to make it look nice. All you're doing is figuring out the C value, right? That perfect value to make it a perfect square trinomial. All right, so I'm going to use my straight edge, which doesn't always work the way I want it to. It immediately did not work the way I wanted it to. The worst part is I actually hit the thing. What is that? Oh, you know what? I'm hitting the wrong icon. All right, that one's on me. Little tracer. There we go. Now let's see if I can do this. I'm going to try to get fancy here real quick. I probably would have been able to yeah, I think it's easier to just draw it. I'm sure for somebody it's easier to do it this way, but not me. I'm just resizing a little bit. All right. So as I'm looking around, because I know that you were asked to do this yesterday, so a good number of people have it done, and I understand why those folks are talking. But the people who don't have it done, I don't understand why they would stop doing work because you would want to have answers. So, I don't know, just thought, thinking out loud, just spitballing here, which sounds disgusting, but it's not. So anyway, I took my rectangle here and I just replicated it 3 more times. But the big question becomes, well, how would I know to do that? And this goes back to the Desmos activity, all right? So that big square is a perfect square with dimensions x by x, right? Its area is x squared. All right, so that gives you the first piece of your trinomial. All right. Now, we're not in a geometry course, but you should know that opposite sides of a geometric figure are congruent depending on the type of figure. So we're talking about squares and rectangles. Opposite sides of squares and opposite sides of rectangles are congruent, aka equal in length. So each one of these sides has a length of x. All right. Now, I just created 4 rectangles. All right. So these 4 rectangles have to add up to equal 4x. What that means is that each one of their areas has to be equal to x. That's the only way that they're going to add up to give us a total of 4x. All right, if you know one of their sides is equal to x and the area is equal to x, what's the other side? 1. So each one of these are going to have a dimension of 1. All right, so this is where the idea of completing the square comes into play, because what I want to do is actually complete the square, physically complete using single unit squares. So 1 unit squares, squares with area of 1. That open space. All right, so the only way that that's going to play out would be, oh boy, there it goes, got it back. Back in the game. All right, so each one of these has a dimension of 1. Dimensions of 1 giving area of 1. All right, so gorgeous looking picture. It must mean that the c value has to equal 4 in order to have a complete square. All right, so I'm going to bring it in a little bit and make a note. All right, so what is the length of this side? X plus 2. The horizontal side, also x plus 2? I mean, if we're completing the square, so all sides should be the same. If I want the area of the whole thing, it should be x plus 2 squared. All right, so what we have here is a visual, I almost said visible, visual representation of what we did on the previous page. All right, because this holds up because this value is half of the 4 in the 4x, and the 4 that makes up the c value is the squared value of the 2 in the binomial. All right, so that plays out for pretty much every other problem. All right, so I'm going to check this tomorrow, but what I'd like you to do is the remaining problems on this page. Some of you have already done it, which is great, but I'm actually going to come around and check this one. All right, so 2, 3, this is all I'm going to check, but we are going to move on and talk about how to complete the square when you're dealing with something that's not a perfect square trinomial. All right, but I want you to, because I'm looking for good pictures. That's really what I'm getting at. All right, so not sloppy drawings. All right, so if it kind of passes my sensibilities as I walk around, like, oh, okay, that's not a terrible piece of garbage, full credit. If I look at it and be like, ah, you just slapped that together, then you're talking about a reduction in credit.
How do we know where like split it up, you know, if there's nothing there?
If there's nothing there, you could always have an x squared. Start off with the same x squared. So reproduce. All right. Your key's posted online, so there really is never any true secrets, but you can do that if you need. So I'm going to take you through a completing the square example. If you follow this process, you're never going to have trouble. I'm going to expose you to it today, and then we'll hit it hard tomorrow. So we have x squared plus 10x plus 9 equals 0. It's a quadratic, because we're applying this to solving quadratic equations. The first thing that we're going to do is move the c value to the other side. All right. What do I mean by c value? Every quadratic is in the form of ax squared plus bx plus c equals 0. All right, so I want to subtract off that 9 from both sides. So we're looking at x squared plus 10x And then I'm going to leave a little blank. And it's going to be equal to -9. All right. Now it's an operation. It's telling us to take whatever the b value is and chop it in half. All right. So here's my b value. So I need to take my b value, chop it in half, and square it. So I'm doing 10 over 2, and I'm going to square that. What do I get as a result? 25. All right. We need to add that to both sides of the equation and then simplify. All right. So x squared plus 10x. I have my little blank there. I'm going to add 25 to both sides. And then simplify. So x squared plus 10x plus 25 equals 16. All right. Next up is to factor the left-hand side of the equation. Now it's a perfect square trinomial. When we're completing the square, we leave off words, but it's completing the perfect square trinomial. All right? We've successfully done that because what we did was we created this relationship where if I were to cut this in half, I would get a value to put in my binomial. That squared value would give me the 25. So my factored form would be, on the left-hand side, x plus 5 squared equals 16. All right. Next step is to actively take the square root of both sides of the equation, which means that there wasn't a radical already there. I'm introducing one. What is the square root of x plus 5 squared? Just clean x plus 5, because the root and the power of 2 are going to cancel away. What's the square root of 16?
4.
Close.
Plus or minus 4.
Plus or minus 4. For two reasons. One, because it says to do it right there. Second, because that's how math works. All right, 4 times 4 is 16. Negative 4 times negative 4 is also 16. Write two separate equations. My voice cracked. We'd have x plus 5 equals 4, or x plus 5 equals negative 4, and solve those. So we're looking at x equals negative 1, or x equals negative 9. So I'd state my final answer, x such that x is, I like to write the more negative one first, negative 9 or negative 1. And that is completing the square algebraically. Anytime you incorporate fractions, it becomes a mess. So we start off pretty easy, but you can also see how this would work out with the actual square.